How many of you, when you were a kid, had a prism that you played with? I did. I'm raising my hand right now. I had a prism. My parents got me this little science kit when I was probably, oh, I don't know, 11 years old or so, something like that. Might have even been little bit younger than that, but part of the science kit was this little cheap prism. It wasn't even a nice prism, but it still worked. And it was just so fascinating to me how a prism worked. I would go outside and just lay on the grass in the sunlight with a piece of paper and my prism, and I would shine the rainbow colors down onto the piece of paper. And it's just amazing to me how this little piece of glass could take sunlight and make a rainbow out of it. It was really a really cool thing to do, and I would encourage you that if you have little kids to get them prism. I have not got one for my kids yet, but when they get a little bit older, I will most definitely be getting them a prism to play with. What a prism is doing is it's separating out the different components of light. So white light consists of all the different colors of the rainbow. One of the interesting things about light is that it will travel through materials differently based on its wavelength. And also based somewhat on the shape, and that's kind of again why this sunlight comes out as a rainbow here. It's partially because of how the light travels through the material, and also partially because of the shape of the material. The shape is what mostly helps it separate, but then it travels differently, which also helps with the separation. But anyway. So the white light goes into the prism. It gets separated as it goes through the prism, and so it comes out the other side not all together. It comes out separated into its individual colors. And so if you take a white light source, like a flashlight here with an incandescent bulb, this is what you see. You see all the different colors of the rainbow. If, on the other hand, you don't use a white light source, if instead of using that incandescent light bulb where you just have a piece of metal and you are putting current through it to the point where it gets so hot that it glows, if instead you have a gas, like hydrogen gas, for example, and you put it in a mostly evacuated tube, and then you put a high current, or high voltage, across that tube. So you have a super high voltage from one side to the other, which excites the molecules inside there, the hydrogen atoms. And when they do that, they start to glow. Very similar to the white light source, but it's a little bit different because when the hydrogen starts to glow, it doesn't give off all of the colors like the white light source did. Instead, what the hydrogen does is it gives off very specific wavelengths of light, and only those wavelengths of light. It gives off a red wavelength, a bluish green, a kind of bluish purplish, and then a more purple color wavelength of light. And it only gives off those wavelengths. And any sample of hydrogen will do the exact same thing. Neon does something similar. If you put neon into a partially evacuated tube, pull a vacuum, put a high voltage across, it will also give off only very specific wavelengths of light, but now there's a lot more. It's not just those four, there's a whole bunch of them. And if you continue to go to more complex atoms, you'll get even more lines of light that are being given off. Only certain wavelengths are produced for hydrogen, and these are 410, 434, 486, and 656 nanometers. Only those four in the visible spectrum, anyway, are given off. And there's a guy whose name I cannot remember for some reason, but he realized that these wavelengths of light fit this equation. So this equation describes the energy of the photons that are being given off at these wavelengths. And so all this stuff in here, this is a bunch of constants. So you have Planck's constant, the speed of light, and I forget what, and actually that should be r sub h, not r times h. But all those constants multiplied together give us this. So we have all those things give us that. And those n values are always whole numbers. So 1, 2, 3, 4, not 0. They're never 0. So they're always whole numbers, which I believe whole numbers don't include 0. That would be integer values would include 0, if I remember my math theory. Anyway, so there are 1, 2, 3, 4, and so on are the whole numbers that the n values can be. What they realized, because these n values are always whole numbers, they're never fractions, never some decimal value, they're always whole numbers, this means that the energy of electron transitions are quantized, which means that the electrons have quantized energy levels. And this is a really big deal. If it's not clear right away, let me explain a little bit more. So in hydrogen, which only gives off those 4 wavelengths in the visible spectrum, and we're only showing 3 of them here. There's another one down here somewhere, but we're only going to look at these 3. These 3 wavelengths of light that are given off by hydrogen, when you excite the hydrogen atom and you cause it to give off light, the reason that it is only giving off these very specific wavelengths of light is because the electrons, which are giving off the light as they move from one place to another, can only be at very specific energy levels. They can only have very specific amounts of energy. The amount of energy that they can have is not, they can't just have any energy they want. There are very specific energies that they can have, very specific energy levels that they can be at, and they're not allowed to be anywhere else. So if, for example, we have some hydrogen in the tube, we excite the gas by putting a really high voltage from one side to the other, and there was an electron down here, and because we excited it, it goes woo, and it jumps up here to this energy level, which we're just going to call 4. Just going to call it n equals 4, just for now. It doesn't really like being up here. Because if you remember, one of the things I always say is the universe is lazy. Nothing wants to be at a high energy level. And so as soon as it gets the chance, it is going to leave, this electron here is going to leave the 4th energy level and drop down to some other energy level. If, for example, it drops down to 2, what will happen is it will give off this wavelength of light to do that, because the energy difference between 4 and 2 is exactly equal to the amount of energy that is in this color of light, to a single photon of that color of light. And so when it drops down from 4 to 2, that's the color of light that it gives off. If you remember the first law of thermodynamics, you can't create or destroy energy. And so if it wants to go down to that lower energy level, it has to give off that energy somehow. And when electrons give off energy like that, they do it by giving off a photon. They give off light. And so this energy transition, going from the 4th level to the 2nd level, is a bluish-green photon. That's how much energy it takes to drop. Same thing here, going from 5 to 2. This drop, because it's bigger, there's at an n equals 5, that's a higher energy than n equals 4. And so because there's a bigger drop here, you have to give off higher energy light. So you give off a violet color photon. If you're just going from 3 to 4, that's not as much of a difference. It's a smaller drop. And so because of that, you only have to give off red light. Not nearly as much energy. And so we know, and this was discovered a long time ago, we knew that the energies of electrons are quantized because we were getting these line spectra. If the energy of an electron could be anything in here, if we could have an electron that was at 4 1/4, 4 1/2, 4 3/4, anywhere in here, then we would just have a rainbow of colors again, because we could have stuff anyway, at all the levels in between. But we don't. We don't have a rainbow of color. We only have very specific wavelengths. And those wavelengths correspond to the differences between these energy levels that the electrons can exist in. So the key thing here is that the electrons have very specific energy levels that they can exist in, and they can't exist anywhere else. They can't be halfway in between the 4th and 5th energy level. They're in one or the other. And even when they move, technically speaking, they don't exist in between. They're not like a baseball that, is here and then gets thrown to the next one down. They actually don't exist in the space between. They're here and then they're here. They're there at one moment in time, and then the next moment in time they're down here. They don't actually exist in between. And as they move, as they go from here to here, they give off the light that is necessary to do that. So it is a bit weird. I know that it's kind of a weird thing to think about, but this is a really key thing as we're going forward and talking about electron configurations. It's very important to realize that the reason we can write an electron configuration is because there are only very specific places that electrons can be. And we know all of them. We know all the places that they can be. And so we can write a configuration that describes where electrons are inside of an atom. All right. So we will end it there for this video. In the next one, we're going to talk about de Broglie, which I believe is how you pronounce that, or de Broglie, if you are American. But I believe the French is de Broglie or something along those lines anyway. So we will pick up there next time.